derivatives have been too easy. Let's make it harder.
Perfect.
Well, maybe. So we are going to cover right now 3.5. Implicit differentiation. And logarithmic differentiation. Wrong topic. Let's start with implicit differentiation. Let's start talking about ways. A function may be defined in two ways. One is the first one you guys are obviously familiar with. It's the one we introduced in the first place, and it's called an explicit way to represent a function. So we call it explicitly. This means y equals a function of x. Right? We say y is explicitly defined. Right? Why do you say it's explicit? Because it's out there in the open. There's my y. On the other side, there's some rule with only x's. Right? This is called an explicitly defined function. Right? This is the form we're used to, and it's what all our derivative rules so far are based on. Right? Depending what the f of x looks like, if it looks like an x to the n, or it looks like an e to the x, or it looks like an ln x, I can tell you what the derivative is, right? And it's explicitly defined. I have rules that I can apply to this guy. There's another way to define a function, though, and it's called implicit. Now, implicit means the y is not explicitly defined. It's not out there in the open. It's kind of mixed up. Things are jumbled. So it looks like some function where there are x's and y's mixed up together and equals some constant, for example. So this is like the y is hidden. Y is hidden in some function. Right, so examples of implicit functions would be things like x squared y plus 2xy equals 3, or xy equals 1, or radical of x plus y equals 2xy squared, etc. Right? So here you see I can write a function, but the rule is not so clear because there are y's kind of mixed up into things. You don't have a y explicitly defined on one side. He's not out in the open by himself. He's kind of mixed up in everything.
Is this where you would use a system of equations to solve it?
Nope. These are just, we only considering things one at a time, one equation at a time. But the problem is sometimes there are y's mixed up. Now there are times when you can move from an implicit form to an explicit form, like for example in these two guys here. I could just like factor out a y and solve for a y, right? But there are times when it's actually a lot harder. And we still want to be able to, for example, find the rate of change of this function y here, but it's mixed up. How do you actually do that? That's kind of what implicit differentiation is about. In case 2, if we want to find dy dx, that's the derivative of y with respect to x, we must use what's called implicit differentiation. It looks really, it sounds really fancy, but really this is just an application of the chain rule. That's sort of how we're going to use things. That's sort of how we're going to figure things out. Really this is just application of the chain rule. So let me show you an example of what I mean. At the end of the day, there's really something simple that you're going to think about when doing this, and I'll explain that. So say the following. Say y equals some function of x, right? I don't particularly know what the function is. What's the derivative of the following? With respect to x. Okay, so let's say I have an example here. The function y itself, b, the function y squared, c, radical y, d, x squared y squared, e, x over y. We're just going to illustrate what we're doing with these guys, and then we'll sort of figure out some general rules of how to apply to this scenario. A lot of times in nature, when we're setting up functions for things, they don't come out nice. Things can be kind of jumbled, but we still need to be able to figure things out. As well as this will also help when we're not dealing with functions, like equations of circles. Those aren't functions, but we want to be able to find a derivative sometimes, and other curves that can be just as messy. So for example, here I'm thinking of y as a function of x. I'm not telling you what that function is, but what would be the derivatives of all these functions, right? So in part A, if I ask you what's the derivative of y, what would you say? Right, that guy is just y prime. Right? This is just the answer. Right? Y prime equals f prime of x. Whatever. Right? So it'll just be y prime. So if I see a y and I want to differentiate it, I just write y prime. That's the derivative by definition. Okay, so that wasn't so bad. What about if I ask you about something like y squared? How do you think of that? How do you differentiate that? Well, remember that this is just this, right? There's a whole function here, and I'm squaring it. How do we do that? Differentiating we get. So if I look at this, well, how would I differentiate this?
So you could say two things, y equal, or u equal to y, and then u equal to whatever squared, u squared.
I mean, whatever. You don't really need the variable thing, but yeah, let's say I said u equals this. What would u prime be? 2 times? Times f prime, right? That's what the chain rule tells us, right? You differentiate the outside, you multiply by the derivative of the inside. So this could be whatever. This could be x cubed plus 12. Whatever, you're going to bring the 2 down, leave the x cubed plus 12, you're going to multiply by the derivative of the inside, right? Now notice here, if I'm looking at my y as a function of x, what this would mean is that I just had 2y times y prime. Right? So I look at y itself as something happening with a function. I'm going to differentiate it using the regular rules because it's kind of like differentiating an outside function. But because this guy is not a variable, it's like a whole function that's built in, I have to multiply by the derivative of that function in order to take the derivative because that's what the chain rule says I have to do. Similarly, what about this one?
So you could undo the radical, y to the 1/2.
So let's say I had u equals radical y. What would u prime look like?
1/2 y, negative 1/2.
1/2 y to the minus a half
Yeah.
times y prime. Okay, make it a little bit harder. X squared y squared. Right, so now this function is x squared times y squared. Now remember, the x is just an independent variable, in differentiating with respect to x. But this y, there's a whole function in there. How would I find what b prime? The product rule, right? Here I have two functions being multiplied. I have an x squared times a y squared. So I have to do the product rule. So what does the product rule say I would have to do here?
F prime times.
All right, so this is like my f, that's like my g, so what I'm going to do, f prime, which is 2x,
Times y.
and I leave this alone, plus,
Two y.
now I leave this alone, times,
G prime, 2y.
what's going to derivative of this?
2y.
No.
2 dy dx. No.
Nope.
2y times y prime.
2y, y prime. You apply the derivative rule, and then you multiply by a y prime. It's basically the idea I want you to start getting. So look at this one. E. Let's say my u is equal to x over y. Differentiate that. What do we need?
Just 1 times y.
What are you using here?
The quotient.
Quotient rule. It's a division of functions, right? It looks like a variable, but remember, the y, there's really a whole function there. It could be whatever, right? So the rule says what? If that's my f, and this is my g, then my derivative would look like what?
F times g prime.
No.
F prime times g
F prime times g.
minus f times g prime over g squared.
Right. So now what would this look like? F prime is 1 times g, which is just y, minus f, which is x, times g prime. What's the derivative of y? 1 y prime. Right? Every time you differentiate the y, you're going to attach a y prime. Over
Y squared.
g squared, which is the y squared. So this is actually y minus xy prime over y squared.
I'm a little confused on why we have to multiply by that y prime.
The chain rule.
So we're sneaking in the chain rule after.
Yeah. The thing is, I write a y, but I really mean there's an f of x here.
No, I get it, but like no. Also for d at the end you said like I know the derivative of y squared is 2y
Yeah.
times y prime.
Yeah.
Okay.
So, I mean, imagine if I actually told you what that function was. Right, so this guy here, x squared, y squared. Imagine that you knew ahead of time that your y was y squared plus 1, x squared plus 1. Right? Let's say you knew that. What would the derivative of this be? This is actually x squared times x squared plus 1. Right? Now if you're trying to find the derivative of that, you differentiate this, well, you'd multiply it, but let's say you wanted to use a product rule. You differentiate this, you'd leave that alone, plus, I should make this something you have to use the chain rule for. So it's not completely silly, even though we could have done it. Okay? So you differentiate this, you leave this alone, right? Plus, what do? You leave this alone.
5.
it doesn't, I should have a y squared. Sorry, that should be a square. Right, so y squared, right? So now I leave this alone and I differentiate this. Now what would the derivative of this look like? Well, it's going to be 2 times this times the derivative of the inside, right?
Okay, yeah.
Now if I start to rewrite this in terms of y, what would this look like? This would be a square. This would be 2x. What is this guy? That's just that y squared hanging out. Because my y is this. Plus here I have my x squared times
Y times Y prime.
2 times y. And this guy here is my y prime. Right? Because this is a hidden function. Every time I differentiate this, I have to multiply by the derivative of the inside. Right? So this y squared is not just a y squared, it's a whole function squared. So when I differentiate that, I have to differentiate the outside, multiply by the derivative of the inside.
So how do we know when to multiply by the derivative when, let's say, we're using a product rule for something?
Well, that's where I'm going to put it now. So note here, we are trying to find dy dx, meaning x is the independent variable. While y is a function of x. So any function y is an outside function. And the chain rule applies. In short, the following is this. Given some implicitly defined function, you have x's and y's jumbled together, right? Defined dy dx. Differentiate as usual, following all derivative rules, right? So just because I'm mixing things up doesn't mean I can ignore the fact that the quotient rule exists, right? I have to obey all the rules, the quotient rule, the power rule, the product rule, these all still exist, following the derivative rules. But every time you differentiate a y function, multiply by y prime. Right? So every time you differentiate a y function, attach y prime to it. Right? Because basically what you're doing is you're applying the chain rule. We're going to do some more examples so you guys can get used to the idea.
Yeah.
It's kind of weird seeing for the first time right now. Because you like see it's just one variable, it's just a y. It's not really a y. There's something there, we just don't know what it is. But we still want to be able to find the derivative of it, because you know derivatives are important. So let's talk about some general cases. There are cases either implicit or explicit differentiation can be used. Example, let's say I ask you this I gave you this function and I ask you to find dy dx. Now there are a couple ways I could go about that. One, I could do it the explicit way, right? Which is the ways we've always been doing this from before today's class, right? So one thing I could have done is I could realize, well, if x times y is 1, then for sure x cannot be 0. So I can actually solve for y. If x, y is 1, this means that y must be 1 over x. Now that's just an explicitly defined function. Now I can find dy dx. The derivative of that would be what? What's the derivative of 1 over x? No.
1 prime, well, 0 times x.
Are you doing the quotient rule?
Yeah.
Overkill.
Negative x
Times y prime.
minus 2.
That's the derivative. See 1 over x? It's x to the minus 1. Apply the power rule, right? Don't need the quotient rule. Remember, the top or the bottom is a constant. Quotient rule is a waste of time. Right? Just bring the thing up, apply the power rule. So that's the derivative. And I'm done. That's it. So I could have done it that way, or two, I can do it implicitly. That is without solving for the y. Right? So I could say, well, if x times y equals 1, what I can do is just differentiate both sides. If they're the same functions, they must have the same slopes everywhere. So I'm going to differentiate both sides. Now if I'm differentiating this is x times a y, which means the product rule would apply. So what I'm going to do is I'm going to differentiate this, leave that, 1 times y, plus, then I'm going to leave the x, differentiate this. The derivative of y is y prime, equals derivative of 1 is 0. And so what I can do now is I can actually, because I want to find dy dx, I want to solve for this y prime. That's what I want to find. So this means that xy prime equals, move this over, minus y. And this means that y prime is equal to minus y over x. Now you might be saying, well, is that the same answer? And of course it's the same answer, right? Note. This is the same answer as before. This is the same answer as before. Since we can see y is equal to 1 over x, so if I have minus y over x, that's just minus 1 over x, which gives me that minus 1 over x squared, right? So I actually got the same answer. This is actually the same as that answer, right? These are both the same things. Yeah.
Where'd you get negative y?
I solve for y prime. Move this to the other side. I subtract y from both sides. Then I divide by x.
Wow.
Right? So we've been used to doing it this way, the explicit way, right? So you solve for y, here's your function, you apply some rule that you know to differentiate it, right? Here though, I didn't solve for y, I just started differentiating everything, right? But I applied the chain rule when anytime I differentiate a y, I multiply by a y prime, right? So I went through, applied the product rule and did whatever, right? So here, I found the derivative without actually knowing what the y was, right?
Can you write that out again?
Huh?
Can you write that? Can you translate what you want again?
Oh, like right here?
Yeah.
In general, no. In general, you won't need to. And by the way, when you have to do implicit differentiation, it's going to be obvious.
It'll tell you.
So, no, but it'll be obvious, trust me. Right? So now, here was a case where I could do explicit, I could do implicit, I could decide to solve for the y, I could decide to not solve for the y. And either way, right? If with something like this, xy equals 1, I would have just solved for the y and take the derivative, right? Sometimes, of course, if life would be too easy with that, it's hard to solve for the y. Heck, sometimes it's impossible to solve for y. And then all your old derivative rules go out the window. So what now? We have to stop calculus because I can't solve for y? Yes, let's end calculus. No more. Nope, we still need, calculus is important. We still need to be able to find answers. So for example, if I gave you this particular function, I wanted another example where technically we could solve for y. So, example, what if we wanted to find y prime here? Given that this function, right? So throughout some sort of experiments or whatever, I know there's a function that satisfies this equation. And I need to find y prime. I need to find the rate of change of y with respect to x for a function that satisfies that equation. Now, technically, we could solve for y. The question is, would you want to? How would you solve for y there?
Subtract the parentheses 5x squared plus 2x times y, bring that over to the other
Nope.
side, and then divide both sides by x to the power of 4. Oh, and then take the square root of y.
Then you'd have y's on that side. You'd have y's on both sides. That's not solving for y. Right? So for example, I could have x to the 4th. You're going the other way. You need to move the 4x cubed to this side. 5x squared plus 2xy minus 4x cubed equals 0. Does anyone see how to solve for y?
Divide by 5x.
You can use the formula.
Quadratic formula. It's a quadratic. I have ay squared plus by plus c. So y would be minus b plus or minus the square root of b squared
Okay.
minus 4 times a, which is x to the 4th, times c, which is minus 4x cubed, all over
Really?
2 times a. So yeah, I could solve for the y, and I could differentiate that with the quotient rule. Do I want to though? No. I'd rather not solve for y and be able to differentiate that. And it turns out I can with implicit differentiation. Right? So, did I say where I have to write this up? So you can imagine, first, a lot of people wouldn't see that you could solve for y doing this. So that's the first major hurdle. Then when you get here, you're gonna have to do a quotient rule with a crazy chain rule inside it. That's not a good time. Right? But with implicit differentiation, I don't need to solve for y. So let's say I had this guy, 5x squared plus 2x times y plus x to the fourth y squared equals 4x cubed. So remember the short rule here, right? The goal is differentiate as usual, obeying all your rules, but every time you differentiate a y term, attach y prime to it. That's basically what the summary of this is, right? So I'm going to differentiate this. What do I need?
The chain rule.
Product rule. I have one function times another function. So I'm going to differentiate this, leave that alone, plus leave this alone, and differentiate the y, which is just y prime, right? 1 y prime. Plus, here I need another product rule, so I differentiate the x, leave the y squared, plus leave the x to the fourth, differentiate the y squared, which becomes 2y y prime, because I just differentiated a y function. Every time I differentiate a y function, I attach a y prime. Equals, differentiate this side, I get 12x squared. Right? So here, I applied the product rule, differentiate one function, leave the other one, then differentiate this and leave that, I got this guy. Again, apply the product rule here. Differentiate the x to the fourth, leave the y squared alone, plus leave the x to the fourth alone, differentiate the y squared. Now remember, the y squared is like an inside function, right? It's a whole function squared. So I'm going to differentiate the outside, multiply by the inside, so I attach that y prime, right? Every time I differentiate a y function, I attach a y prime to it. Over here, there's just x functions, right? Now if I want to find y prime, what do I need to do? Well, now it's just a matter of solving the equation for y prime, right? It's algebra from here on out. I just need to solve for that guy. So what I'm going to do is, everyone who has a y prime, I'm going to leave them on one side. Everyone who doesn't have a y prime, put them on the other side. So the y primes, I have a 5x squared plus 2x times a y prime plus 2yx to the fourth times a y prime equals, everyone without a y prime, throw them over there. And then I have a 12x squared minus 10x plus 2y minus 4x cubed y squared. That's it. And so this means my y prime is, I figure I want to write this all again. 2x squared minus 10x plus 2 times y minus 4x cubed y squared over 5x squared plus 2x plus 2y to the fourth. So that's actually my derivative. Now, you can take a second. It's a little tedious with algebra, but consider the fact that every time I write a y down here, it's actually this huge thing right here, right? So imagine if you were doing the quotient rule and simplifying it. Imagine the kind of monster that you're going to get over here. It'll be, you think this was painful? No. Differentiating that with the quotient rule would have been painful. Right? But the idea is, with the power of implicit differentiation, I don't need to solve for a y. I just go through my regular derivative rules. Every time I see a y, every time I differentiate a y function, multiply by y prime. If I find the derivative of an x function, I don't do anything. Yeah.
So maybe I must have missed something. The way you can factor out the y prime in your next step, basically, so correct me if I'm wrong, but basically you just subtracted 10x plus 2 times y
Yeah, I
on
took
both
this,
sides.
move it over there. Yeah.
And then subtracted the negative 4x cubed y squared.
Yeah.
And then you factored out.
And then I factor out a y prime. It's algebra, distributive law. Yeah.
Sorry, I just missed that completely.
Let's do some other examples. Right? So here was a case where I could have solved for the y prime, but it was horribly messy. I wouldn't want to do the quotient rule on that guy, so I did that. An example where it's not difficult or annoying. It's literally, it's impossible to solve for the y. Right, so let's say I had a function that had this relationship. Find dy dx given this thing. X squared plus y to the 7th minus 2y equals 3. By the way, that's not a completely crazy curve. I actually drew the picture here. That's what it looks like. Technically, it's not a function because it doesn't pass the vertical line test, but it would look similar to that. Right? So a very innocent looking curve. That's the equation it's going to fit. Now, if you want to solve for y, that's impossible. It's a 7th power. I don't know how many of you know about how polynomials work, but you know like how you have a quadratic formula? There's a formula for if you have cubes, there's a formula for if you have quartics, 4th powers, there's a formula for if you have 5th powers, but after that, no formula exists, right? Like in general, if you have a polynomial where the degree is 6 or higher, there's no formula to solve for it. It's like, you try something, it might work, it might not, you don't know, it's like a toss-up, right? In this particular equation, like, yeah, I cannot solve for that y to figure out the derivative. I'm stuck with this. So now I'm just going to have to figure out how do I get y prime knowing that? Well, differentiate both sides. So derivative of x squared is
2x.
2x plus derivative of this 7y to the 6 y prime. Every time I differentiate a y function, I multiply by y prime. Minus
2.
y prime. Every time I differentiate a y function, I multiply by y prime. Equals 0. That's derivative 3. Now I want to find y prime, which is my dy dx. That's this guy. Now I'm just going to solve for him, like algebra. Subtract that 2x. I'm going to have 7y to the 6 minus 2. All of that times y prime equals minus 2x. And so now my y prime is just minus 2x over 7y to the 6 minus 2. So that's the function that gives me the slope of the tangent line at any point x comma y. Now, note here that I still can't solve for y. So you see this y that I wrote here? I still don't know what the heck that is. But the thing is, I don't really need to know. Because if I ever need to find the slope at a certain point, I can figure out the particular value that would work, right? So if I want to say, what is the tangent line at x equals 1? Well, I go here, plug in x equals 1, figure out some y values, probably use a computer to guess numbers for me. And then I plug that y value here, plug in 1 here, and that's my slope of my tangent line. Oh, and I did ask that. I asked for the above. Find the equation of the tangent line. It's not going to be that bad. I said 2 comma 1. Okay, so what do we need for the equation of a tangent line? We need the slope. Where does the slope come from?
The derivative function.
It's the derivative function. This is actually dy dx when x equals 2 and y equals 1, right? Because I gave you the coordinate, x is 2 and y equals 1, right? So in other words, that's going to be, I'm going to go here, I'm going to plug in 1 for x. And I'm going to 2 for x, because x is 2. And I'm going to plug in 1 for y. That's minus 4 over, what is that, 5? this means? What's my tangent line?
Well, y minus 1 equals the negative 4/5, open parentheses, x minus 2, and then distribute.
No, I believe that.
Oh, okay.
That's my tangent line. So yeah, there are times, well, before we just had functions in a really nice form that we call the explicit form, and we had all our formulas to deal with that kind of form. But sometimes things can be mixed together. And sometimes we can't even solve for the variable that we'd like to solve for to be able to analyze that function. And so that's why we need some like implicit differentiation. And it really uses the chain rule. It's just an application of the chain rule.
Professor,
So, yes.
now all of this implicit differentiation doesn't only work with, like, let's say crazy stuff like with only like 2 variables with like x's and y's mixed in, or can I throw in
Well,
like,
it'll work all the time, but
so
it's
like
not really
throw-
useful if that's like your x's and y's are mixed up. That's why I said it'll be obvious when you have to use it. Like if someone asks you to find the derivative and your x's and y's are all jumbled up, you're like, oh, implicit differentiation, right? If it's just like y equals and there are only x's on this side, not implicit differentiation. Is basically gonna be how you're gonna look at it. And
So
usually like in like a final, that's how it'll phrase. So they like differentiate. Right? It's like problem 1 or 2 on the final. And part A would say something like y equals x times the radical of x squared plus e to the x. And then part B is like, y equals ln x over e to the x plus 1. And then they're gonna like part C, y equals e to the 2x squared minus 7x squared. And then they're gonna be like D xy plus 3x y cubed x plus 7x equal radical x. Right? Explicit, 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 implicit. The y's are mixed up. Right? You can see your x's and y's are together, they're jumbled up. Everyone else, you only had a y. The y was by himself, and there are only x's to deal with here. We can apply rules here. Right? But here's like my y and a y cubed and everything, right? That's your implicit differentiation guy right there. You're not going to say, oh, this, by the way, part D is implicit. You have to figure that out, because for you have to realize that I can't solve for y here, right? So basically you just start differentiating both sides, and every time you differentiate a y function, attach a y prime to it, and then solve for it using algebra afterwards. So it will be obvious when these things happen.
Well,
And by the way, equations like this happen all the time. You might think that, oh, do we really have to know this? I mean, for example, here's a famous equation in chemistry. This is called van der Waals equation. Always forget it. Right? V here represents the pressure of the gas. P represents the pressure of the gas. V represents the volume of the gas. And it turns out that that's the relationship they have together. Right? Now you can figure that out through experimentation, but at the end of the day, you know that's the equation. So here, if someone asks you to find I think I asked dp dv. Or no, I asked dv dp. Right? In other words, what's the rate of change of volume with respect to pressure, right? So I'm saying as pressure increases, what happens to volume? Or as pressure decreases, what happens to volume? How does the volume change when the pressure is changing, right? You can answer that question for a gas that satisfies that equation. How would we figure that out? What is dv dp here?
So do we need to get d alone?
Where?
Well,
You have to get v prime
Right. So first thing we have to remember is who's the dependent and the independent variable, right? Here notice the p is on the bottom, so that's the independent variable. That's like our x, right? So that's the guy that when we differentiate, we're not going to do anything, right? The v, though, is the dependent variable, so I'm thinking of v as a function of p, right? So that's the guy, whenever I differentiate him, I have to attach a v prime, which is my dv dp, right? Now I'm going to go through and I'm going to differentiate this function, which you might notice is the product of two functions. So I'm going to apply the product rule here. So I'm going to differentiate this term, leave that alone. So what's the derivative of this? Derivative of p?
it's just,
Zero.
Here. One.
One.
1, right? V and p are both variables here, right? That's like an x. Plus, what's the derivative of this?
minus 10 v to the negative 1.
To the negative 3,
Oh,
right? This is 5v to the minus 2. When you subtract 1 from minus 2, you get minus 3. Right, so that's the derivative of that. Leave this alone. Plus, now I leave that alone. And I differentiate this.
just 1. Or no.
Are we missing anything?
Yeah.
Right.
V prime, right? You have to remember V is the dependent variable. So every time I differentiated a V, I had to attach a V prime to it. Every time I differentiated a V here, I had to attach a V prime to it. And derivative of 9.7 is 0. And so now what?
Oil?
v prime.
We want to find the V prime. So everyone without a V prime, I'm going to want to move to the other side, right? First thing I'm going to want to do is get this guy outside the brackets. So I'm going to multiply this. This is V minus 0.003 minus 10V to the minus 3, V minus 0.003 V prime plus P plus V over 5 over V squared V prime equals 0. Gonna move this to the other side.
Wait, what did you?
Wait, what did you? Yeah.
Wait.
What that second row? What did you do?
I distributed. I took this guy here and I multiply by 1, multiply by this.
Okay.
Right? So I have this times 1 is that, this times that is that.
Okay.
And now here are my V primes. This guy doesn't have a V prime, so I'm going to move him to the other side. So I'm going to come over here. He's going to be the negative V minus 0.003. On this side, I'm going to have V prime times all of this. And then just divide. I hope by now you guys appreciate why I started to torture you with algebra at the beginning of this class, the first quiz and the second quiz. so that's my v prime, which is actually dv dp.
Can you go back to like what those little arrows are, how you got the second line?
Okay, so I have this. I want to find dv dp. So I know p is my independent variable. That's like my x. The v would be like the y. So when I differentiate a p thing, I don't do anything. If I differentiate a v, I have to multiply by what? V prime, right? So I go through and I do the product rule here. So I differentiate this, leave that alone. Derivative of p is just 1. Derivative of this, I look at this as 5. I think of this as 5e to the minus 2, and I apply the power rule, right? So the minus 2 came down, made it a minus 10. Subtract 1 from the power, I get minus 3. Since I differentiated a v function, I multiply by v prime. Then I leave this alone. Plus, leave this alone and differentiate that. Derivative of v is just 1 multiplied by v prime. And I end up with here. Now the goal is to find v prime, right? So it means I need to solve for this guy. That's in 2 different locations. So my first goal is to get everyone who has the v prime on one side and get everyone who doesn't have a v prime on the other side. So before I do that, what I'm going to do is this v prime here is stuck in brackets. So I want to get him out. So I expand the brackets. So I took this number times that, this number times that. And that gave me this. This times 1 is this, and this times that is this.
Okay.
Then here, I just have a number times that. And so now, my v primes are out in the open, and this guy doesn't have a v prime, so I took him, I moved him to the other side. V prime is a common term, so I factored that out, and I get this line. And then now to solve for that v prime, I divide by all of this.
It doesn't look hard when you do.
Yeah, the trick is not to be scared by how the things look. It's kind of like, describe this. Let's say this whole thing here was an A, and this whole thing here was a B, and that was an X, and this was an X. Well, maybe it was like a KX or something like that, right? And someone told you to solve for X. What would you have done?
Distribute the A.
Distribute the A, right? It's kind of obvious when you look at it like that, right? It's just this times that, you get A minus KAX plus BX. You want to solve for the X, right? That's equal to 0. You want to solve for the X, so you take that guy, move him to the other side. You get minus KA plus B all times X equals that minus A. And then you just take X equals minus A over. I did the same, it's the same thing, right? The difference is, when I looked at that, I didn't freak out, oh my god, there are negative powers and da da da. No, I just saw there was a number here, I need to expand the brackets. And there's just a number in front of the X. This to me is just a number, right? Once I zone in and I realize I need to solve for this guy, everyone else is just a number. I'm just multiplying out, expanding brackets, moving things to the other side. I just go in algebra mode, right? I don't care about how they look. I just, oh, I need to expand the brackets here. I need to get that X out of prison, right? That's how you want to look at it. Yeah.
So would implicit differentiation work if I had not 5 variables, but let's say more than 2 variables mixed in?
Yeah. Yeah, you can extend it a lot. In fact, when we get to related rates, you're going to see that even more. Let me just give you a couple more normal looking examples. This was just one for you to appreciate that this does happen in real life. That's an actual equation that chemists use all the time. It's an equation that even has its own name. So let's say do this as well. The problem on your test are you're trying to look closer to these ones. I'm going to give you a van der Waals equation. Or something like x squared y plus 2xy3 equals 4x xy. The goal is to find y prime. We'll find a way. Forgot to mention. Just a little side note here. I'm thinking of making S2 either June 30, which is a Thursday, or the following Monday,
Following Monday.
July. It would have to be the following Tuesday because the following Monday is actually 4th of July, so it's July 5th.
Okay.
I'd prefer this day.
Why?
Because the drop date.
The drop date is the 7th,
Oh.
and you know I'll be under pressure trying to grade it.
No.
Um, Yeah, so these more look like the kind of guys you get on a tester, and these I'm not going to go too crazy. So yeah, that's D. Okay, let's do part A. Which, by the way, notice that yeah, part A. Yes, for this guy I need the product rule, so that means 1 times e to the y.
Plus x
X.
times e to the y squared.
Yeah. Right? E to the y was a function of y, so its derivative was itself, but I have to multiply by y prime. Plus
6x
6x equals
2 times y prime.
2 times y prime, because that was 2y as a function of y. Yeah. So now I just have to solve for y prime. That's the goal, to find dy dx. How do I do that?
Subtract.
Keep going, you can simplify that, e to the y plus all that together, plus 6x equals 2.
Simplify how?
Well, the 1 times e to the y is just e to the y.
Yeah. Yeah, I could not write that one.
Yeah.
Yeah, that's fine. But what are we to? You want to solve for y prime. So what's the goal?
Subtract
Subtract.
2y prime.
Right, you want to get all the y primes on one side. So I'm going to take this y prime, move it together with the other y prime. So I have x e to the y prime minus 2y prime.
Is equal to
And then anyone who doesn't have a y prime, put them on that side. All right, so here this e to the y didn't have a y prime. Move him over, it becomes a minus e to the y.
Minus 6x.
And the 6x doesn't have a y prime, so move him over, minus 6x. And now my y prime is a common term, I can factor that out.
Divide.
And so now I just divide by that to solve for y prime.
Professor,
Yes.
so what I'm getting at is e to the power of anything unknown is just exactly that.
What do you mean?
Meaning like e to the power of x or e to the power of y, e to the power of q is the same thing.
Are you talking about derivatives?
Yeah.
Well, no, in general, derivative of e to the u is u prime e to the u. That's in general.
Mhm.
That's with the chain rule, which is exactly what I did here, if you notice.
But e to the y is over here, like,
Right, my y is a function. There's really a function here.
okay.
Right, so it's kind of like if I had e to the x squared, the derivative of that is 2x e to the x squared, right? That's my, this would be my y, this would be my y prime.
Okay.
It's the chain rule that I'm applying.
But you did say that the derivative of e to the power of x was literally just e to the power of x.
Right, because x prime is 1.
Oh, there's something else.
That's e to the x times the derivative of x is 1.
So it stands to reason that the derivative of e to the power of 2x would be e to the power of x times 2.
E to the power of 2x times 2.
Oh.
The original function times the derivative of the power. That's for exponentials. So yeah, in fact, the chain rule always applies. So the thing is, if there's just an x, you multiply by 1. So it doesn't really change anything. I've had students before who were confused about when to use the chain rule, and I just told them, always. Because literally, if you keep doing it, you're just multiplying by 1s. You're not going to change anything if you shouldn't change anything. Man, this one looks really difficult. I don't know about this one. You guys gotta help me out here. Find dy dx. What's the first thing we do?
You can change the radical x right to the half.
So I can rewrite this, right? We don't have any rules that have radicals in them. All the rules have powers and things like that. So I could rewrite that. Sure. Now what?
Half xy to the negative 1 half.
What rule are you applying here?
The power.
You use a chain rule.
You could use the chain rule, or you can write this as x to the half, y to the half, and use the product rule. It's you'll kind of end up at the same place, so it depends on how you want to look at it. So let's say I want to use the chain rule. This is an inside function, right? So bring the half down, leave the inside alone, subtract 1 from the power, then you're going to multiply by the derivative of the inside. What's the derivative of the inside?
Just 1
y prime.
Prime.
No,
No, 1.
no.
Oh, it's product rule.
Product rule. Don't forget the rules. Right? This is x times a function. It's a product rule here. Differentiate one, leave the other. Plus, you leave the x, you differentiate the other one. Plus, derivative ln of y. 1 over y times y prime equals derivative of 2, derivative of x squared, 2x. Now, I need to solve for y prime. I need to get to this guy. But this y prime is inside brackets, so what do you think I need to do?
Distribute.
Distribute. I need to multiply out. Take this number here and distribute it. So I'm going to take 1/2 xy to the minus 1/2 times y plus 1/2 xy to the minus 1/2 times xy prime plus 1 over y prime equals 2x. So now my y primes are outside the brackets. Or I need to parentheses or whatever. So now I need to solve for that guy.
Wait, what did you just distribute? That 1/2?
This guy, this whole thing here, I multiply it out. So I take this times that, this times that.
And then, wait, times x and then times the y prime? Times everything?
Times everything. Yeah, this is x times y prime. So I have x times y prime times this. It's just one big multiplication.
Oh, got it. Okay, sorry.
Now what?
Y prime 1.
I need to get y prime alone, which means this guy's an intruder, moving to the other side, right? So on the other side, I'm going to have 2x minus this guy. And then my y prime is factored out. And I'm going to have this 1/2 xy to the minus 1/2 times x plus 1 over y. And then I just divide by that. So that means my y prime equals 2x minus 1. X squared plus y squared equals 4.
Professor, this is hard.
What's hard?
Like, this is hard work. We should get paid for being serious. I'm so serious. This is.
Well, you'll get used to it. It gets easier when you get used to it.
It's not immediate.
Okay? What do we do here?
2x plus 2y prime equals 0.
Solve for y prime.
Get rid of 2x, so it's going to be
Minus 2x. And then you divide by 2y.
2y.
So it's just minus x over y.
That one's easy.
Yeah, right.
Give us that one.
When a guy like that shows up, it's going to be in like the middle of a word problem or something.
Oh god.
Oh, we're full of words.
Yes.
Word problems are the most important.
No, we don't care about long words.
The llama population is in danger. You think I'd keep them in my house if I didn't have to? Okay, find y prime. How do I differentiate this?
Product rule.
Product rule. It's one function times another function. So,
It's 2x times y plus x squared y prime. And plus now product
rule again, right? It's one function times another function. You derivative.
2 times y to the third plus 3y prime.
3y squared y prime
Right. Plus, times 2
times that 2x.
equals 4y prime.
Derivative of 4x is 4, plus derivative of y is y prime. Now we need to solve for the y prime. So there they are. I need to get all those guys on one side. That's the first thing.
will you subtract y prime on the side with
So here I have x squared y prime. That's this guy. Plus here I have 6xy y prime. That's that guy.
3 to 6.
3 times 2
Oh.
is 6xy minus this y prime.
Oh, that's right.
And those are all the y primes. So now I want everyone without a y prime to go to the other side. This 4 was already on the other side, so he's here. I'm going to subtract this 2xy. So now he's gone. This 2y cubed, I'm going to subtract that. So now he's gone. That accounts for everybody. So now my y prime here is a common term here. So I can factor them out and divide by the remainder. Divided by x squared plus 6xy
minus 1.
Isn't it 6xy squared?
6xy squared. Yes, that's a y squared. I was seeing if Nikolai was paying attention, but he wasn't.
I'm still trying to get my head around this. I'm really
Put
trying.
him in the hot seat. Shame on you.
You guys pick on him too much.
Why me?
Oh, there's gonna be a point where we're gonna make this harder, because we're gonna throw a third variable in there, and then we're gonna start thinking of x as a function of someone else, and then But we need that for like related rates.
But let's work on levels.
Yeah, rather.
Didn't finish this section. I wanted to talk about log differentiation.
No. We still need practice. Yep.
More, can we do more examples?
Start working on these ones. You can look at the old finals and start working on the implicit differentiation ones, which they're going to be obvious. Those are going to be the guys where your x's and y's are jumbled together and they're asking you to find the derivative. We'll stop there. So we didn't complete this section. We will complete it on Monday. And for now, I guess I can take questions on the homework, chapter 2. I believe we have to do 2.3 and 2.4.
Can you do 2.3, question 5?
2.3, problem 5. Which, by the way, let me just mention, for something like implicit differentiation, you probably want to write something like this down. It's like a mini summary. First bullet point. You know you have to use implicit differentiation tell me how you know you have to use it.
Your x's and y's are jumbled together.
X's and Y's are jumbled together. Use whatever language works for you, right? If you wouldn't use the word jumbled, use whatever word you want. Right? X's and Y's are mixed together. I can't solve for the Y. However you want to phrase it, make sure you write down a sentence to know when you have to use something, right? Right, so you would want to know when you want to use a certain thing. Then you're going to want to know how would you use it when you know you have to use it. So how would you summarize what we did with implicit differentiation in like a sentence?
You say, wait,
How would you describe how we did this differentiation to get it in a sentence?
differentiate and solve for y prime.
Right, but what makes it different from differentiating from before?
Every time we differentiate a y, multiply by y.
Yeah. Differentiate as usual, except you differentiate a function of y attach y prime to it. And the third bullet point would be solve for y prime using algebra. Right, so especially if you're going through your notes or anything and we go through a topic and you're slightly confused, what you want to do is you want to be able to write bullet points to yourself, right, in language that you would understand, right, very concise statements or steps to know how you want to approach something. And when you're studying, you kind of always follow those steps. You always kind of try to make it conform to the system that you set up. And that way you don't really get confused. You just know, you go on a test, you see your x's and y's mixed together and you have to differentiate it, you need implicit differentiation. Well, how do I do that? Differentiate as usual, but every time I differentiate a function of y, attach y prime. Okay, then solve for the y prime, right? So once you have the steps clear in your head, the rest of it is mechanical. It's just actually doing the algebra. But even you can see that even when you're doing the algebra, the goal is to really think of it in simple steps. You don't really want to think of something complicated. Because then the math seems a lot harder than it actually is. So it's kind of like, let's write this like I'm just writing craziness here right now.
I'll say that's impossible and hope it's right.
Yeah, like whatever. So the thing is, things might look scary a lot of the times, but you sort of always want to have your kind of blinders on to some extent. So usually, like when I see something like this, really, when I look at it, that's what I see. You know what I mean? So it's not like, so it's like when we had that van der Waals equation, you're like, oh my god, how the hell are we going to solve for b prime? It's because you're looking at it and you're like, oh my god, there's a square and there's a radical and then there's the e to the power xy. No, it's just one thing minus another thing, all squared. Right? So when I'm looking at algebra, I kind of zone out. And so I just know, here's a little complicated mess. As far as I'm concerned, that's just a number. I can expand the brackets. I can do whatever manipulation with it. Right? Your laws of arithmetic and laws of algebra, they work with variables as well as numbers. So when things look scary, you kind of have to look at them in a non-scary way, right? It's sort of the same thing when I had that first example about implicit differentiation when I asked you, how could you solve for y, right? You saw this crazy thing. All I saw was this. It's a quadratic in y. Use the quadratic formula to solve for y, right? But when your a is something crazy, your b is something crazy, your c is something crazy, you choke, right? You just have to know how to look at things, right? So if I'm like, I want to solve for y. As far as I'm concerned, the y's are the guys I focus on. Everything else, they're just numbers. I don't care if it was
How would you solve for that?
What?
How would you solve for that, what you wrote on the board? Aside from a minus b.
No, like if I had to solve this equals 0?
No.
Above it.
Above it.
That.
Oh, well, this is not anything to solve.
Like, for example, you see how you said, like, oh, all I see is a minus b squared?
Yeah. So
Like,
I don't
after
know what
that,
the question would
I
be.
wouldn't know what to do.
So like what if someone said expand and simplify?
Like, I would freak out.
What would you have done here?
Ace.
You'd have done a squared minus 2ab plus b squared, yeah? You're going to do exactly the same thing. Raise all this to the second power, take this times that, multiply by a 2, then raise all that to the second power. The same thing you would have done here is exactly what you're going to do there. Right? It doesn't matter that it looks scary. They're just pieces you're moving around according to some formula that you already know. So. That's just one way you'd want to look at things. I know a lot of people, they get scared by just how something looks and then they choke. Try not to be like that. Anyway, problem 5.
So the question says, the height above the ground of a bullet fired straight upwards is h, it's a function h of t, equals 1400 t minus 16 t squared.
Okay, that's height above the ground of a
Yeah.
bullet that you fire straight up in the air. Okay.
Where t is the time in seconds after the bullet is fired.
Yeah.
Find the instantaneous speed of the bullet 30 seconds after firing.
Okay.
That's it.
So this is 2.3. At this point, we had what? The limit definition of a derivative? Or did we know the shortcut for a derivative? I think it was limit definition.
Yeah.
Yeah, the definition.
Right, so remember that instantaneous rate of change. Is just the derivative. Now at this point, we only had the limit definition, so you would have done this to find your derivative. Not that that's also called h. You could call it something else, so we don't get mixed up. Then as h goes to 0, s of t plus h minus s of t over h. Right, now with the shortcut, you just differentiate it. So you get 1400 minus 32t, and then you plug in t equals 30. But here we have to do the limit definition, which now we can know ahead of time what the answer should be because we're geniuses. So I'm going to have limit as h approaches 0 of, this is s prime, of 1400 t plus h minus 16 t plus h squared minus 1400 t minus 16 t squared.
All over h.
All over h. So this is 1400 t plus 1400 h minus
16
t squared. This is 2 times t times h times 16.
32 t
32
h minus 16 h squared.
Minus 1400 t plus 16 t squared.
All over h.
All over h. Start to simplify, guys. This would kill that.
16
This
t
would
squared
kill
is
that.
Yeah.
So now I factor out an h from what's left over. I have 1400 minus 32t minus 16h all over h. The h's cancel. Then I plug in 0. So I get 1400 minus 32t. Which, power. This implies at t equals 30 seconds, they said? Instantaneous rate of change equals 1400 minus 32 times 30. And that would be in, is that feet? The
Yeah.
distance was in feet? Feet per second.
Wait, what do you do with the 16h?
Limit as h goes to 0, so I plug in h equals 0.
Okay.
So that goes away. Right, so that's how fast the bullet is moving after 30 seconds. Other question?
Can you do 11 on the same section? That's
What does that say?
Use definition 5 to compute the derivative of the function at the given value. You have g of t equals t squared plus 5t minus 2. T equals 4.
I guess definition 5 was something that said where you had g of a plus h minus g of a over h. Was that it? I'm guessing. So where my a in this case, I put in 4. So I'm looking for the limit as h approaches 0 of g of 4 plus h minus g of 4 all over h. So now if I look at g of 4 plus h, I'm going to go here, plug in 4 plus h instead of t everywhere. And plug in 4 here. That's going to be 16 plus 20. So that's equal to limit as h approaches 0 of, I'm going to expand these brackets, that's 16 plus 8h plus h squared plus 20 plus 5h minus 2 minus 16 minus 20 plus 2 over h.
The 2's cancel, the
2's cancel,
cancel,
the 16's cancel,
the
20
8h
cancels.
the 8h and 5h combines to what is 13h.
Right, so I get 13h
Plus 8, yeah.
plus h squared, which I can factor out in h.
13 plus 8.
Which is just 13.
Which is just 13. So now, notice, in hindsight, I could have just found g prime of t, which is 2t plus 5, right? And then plug in 4. And I would have gotten 8 plus 5, which is 13.
Wow.
Aren't you glad we have derivative rules?
Yeah.
You should be appreciative of these rules.
I consider just plugging in the 4 everywhere I saw t or his, yeah, or a in this case, or t in this case, because that's kind of like, it saves that last step. That's one last step.
Yeah. So once you get the answer here, that's, you don't need to plug in anything. But again, of course, if you're doing this like on a test or something, you also should check your answer in the corner with the short way, just as a verification. So time's pretty much up. We're going to do implicit differentiation. Finish that up and do log differentiation, which is going to be pretty cool.
No.
We skipped 3.2.
Yeah.
So we went up to 3. So it's 3.1, 3.3, and 3.4. So there are 3 sections due on Monday. Right, quiz on anything. You guys can pass over.